Ela fosse abrir
da carga que você
pelo menos a definição
de temperatura e de peixe, a gente vai efetivamente um estado de temperatura tomado por fato de massa que oferecer um estado de
você tem não gostou, não se
dessa situação. Ou então, separar o estudo da composição do braçodinho, porque você todo acanhado, porque a câmera está rodando. Esse disco que você fez, 5 anos para trás, você crescer com o braçodinho.
Eu já entreguei a sua namorada.
The summary, the reason it's not uma transição ela vai por efeito de umidade, né? As correntes de umidade elas sem esse buraco aqui, você pode ir é um processo
Não tem nada.
passa longe, né?
Mas agora a dor vai fazer que ele está sofrendo. Tem um monte de músicas lá. Deus está pedindo.
No te preocupes, estoy evitando enfocarme.
aumento una punta ultrasónica para que esos pontes de hidrogênio que você tem quando afastou uma folha do grafite se desprenda para você ter uma folha ou poucas folhas.
Para que você já
consiga ter, é como se você tem um apilamento de várias folhas, aí você oxida ele e se afasta. Só que depois de você afastar, você precisa tirar, neste caso mecanicamente, você sonica ele.
Não pode falar English for both of us. The key pictures.
Small hole, so they really move as close entities from one hole to the other. The voltages, they did not agree that well, but I think there was also the problem in the simulations. We have to add this tau. No, it's not perfect. I mean, I think, let's say, in time there was a very good view that say the frequency where it started emitting signals, it was not the best. But I think it captured the overall physics, and I think it was actually capturing already what we had in mind with it, but still, of course, we could have some more confidence. In numbers, it was not, let's say,
I just wonder if you do a molecular simulation, instead to consider a point, but you consider like a hard sphere, with a software software cognition, right? Should it work for this study?
Yeah, I mean, it could work because the molecular dynamics simulations, let's say, capture the physics. I agree with that. Yeah, I'm not saying it doesn't work, but it captures, let's say, with certain ingredients you directly put in the molecular dynamics simulations. While here, this gives really the reason why, let's say, this kind of behavior is. That's for me the big distinction. You have to be, let's say, I mean, I'm not saying that molecular dynamics is bad, but you have to be careful with which things you put in the system to get your result.
I'm not sure this will work because you need deformable form.
Yeah, it has to be some deform. Yeah, but perhaps you could put that in, let's say, to the host dependent. Yeah, this you have to get, because otherwise you will never get the sort of inertia. And I think it's possible, but then you get into putting too much things in the molecular dynamics simulation, and then it's not, I mean, it will fit your result, but it's meaningless. Here, it fits the main, I prefer it fits the main physics, and you get insight rather than, let's say, getting a fantastic thing. But of course, I mean, still we are using also the molecular dynamics simulation in many occasions, because it's very helpful. Okay, so that was the first part about the ratchet. So the ratchet was, let's say, where does this inertia, apparent inertia come from? Because this comes also from the phase decline, because it's like hysteretic. It's easier, it's much more difficult to create, let's say, the phase decline by applying current than to destroy it. You need to slow current, and that gives this what is called apparent inertia, just a delay because of the process of making and stopping. You have no motion, of course, when the driving force is too small. Then at the first point where it starts increasing, we can see that we have one vortex moving one side. And then of course, if the AC amplitude is bigger, and actually it's easier to go back instead of going through. So this is schematic to show here. So what happens then, and this is causing the dip, the vortex now can go one up and one down, and of course the average motion drops not perfectly to zero, but at least to a very small amount. And this you can go further, so you can go even 2 times up and 1 back, and actually by playing even tilt, you can say I go 7 times up, 6 times back, or 7 times up, 4 times back. So you really can play with this army of vortices, which are sitting in the saddle, which are beautiful vortices, moving them discretely into the saddle. So in the case of our ratchet system, going back to the same saddle as well, you expect this, so you have a rectifier. At a certain AC amplitude, you start rectifying your particles, so they are moving to a preferential direction. It should also have discrete high frequencies. And in this case, indeed, discrete would mean like at a certain frequency you move one step, so you should have a step-like function. So like moving one unit cell every AC cycle, or if you drive in even more, you move in 2, and this have a.
In the time we studied inside. And so I want to explain a little motivation. But usually when people want to explain the motivation to go work, they always show how important work is or how beautiful work will be. But for me, it's a little, I will explain another way. In 2005, I arrived at Brazil. And then I had many plans, very nice plans, to make very nice work. And then the ABCD, etc. But it really depends. Yes, it really. But it really depends on Lebanon or Scripture. Because I was told it was a project, a big project, to build a Lebanon Scripture already approved. So my business is use the Lebanon to make my plan ABCD. But the reality is, until the Lebanon certificate was only in 2010, at the end of 2010. So in 5 years, but I couldn't wait, only we stop everything and wait. I couldn't. I had to do something. Otherwise I would be killed. So, fortunately, in 2005, so one professor from Germany, Professor Hasmikis, donated his machine to us. So I was very happy. So I installed the machine at CBS in 2005. So a very big machine, a very complicated to use, and also very expensive to operate because it needs a lot of electric heating. To prepare one sample, we need at least 100 liters of electric heating. Especially for this, very expensive. So with this machine, we can prepare magnetic nanoparticles, and it has a split coil superconducting magnet, and it has a cryostat to change the temperature from 2 Kelvin to 300 Kelvin. It's very nice for me to study the hybrid system. Then I checked the literature. Then I found out that most of the books are focused on the bilayers or multi-layers or superconducting thin films with degrees of ferromagnetic degrees on top or below. And then, so it's very nice for us to study this kind of properties because few work has been done for such system. So we decided to do such a study. So the preparation is very easy to see, very difficult to do. So we just do a coolization of cold nanoparticles and lead on a very cold substrate. Here we use sapphire. Unfortunately, the machine can produce really nice magnetic nanoparticles. For example, here I show the picture of cold nanoparticles. We can see the diameter is very close. So it's like 4.5 plus or minus 1 nanometer. So it's really nice. And then with all the work I've done, the main result is the magnetic nanoparticle. The small particle with only 5 nanometers can induce spontaneous vortices. So this work, in fact, I got a lot of help from here now. And so it can induce spontaneous vortices. You forward particles it will change for sure. But when the magnetic field is very small, only depends on the orientation of forward particles. Of course, we still have the proximity effect and the formation of spontaneous vortices. So the density will decrease. So if we compare our sample with the only proximity effect, so here this line is copper nanoparticle inside the lead. So we have cobalt and they have copper, and the diamonds they are almost exactly the same. This comes from graduate. And then you see, and even you can reach 70% of copper volume fraction. Volume fraction of copper can reach 70%. This field has very sharp transition. It's like a 3D resolution problem. But our sample is very different because of the formation of spontaneous vortices. So the effective volume increased a lot. It's not only the cobalt particle, but really the vortices. So we don't need a lot of cobalt particles to kill the superconductivity. We just need only 7%. But if we really compare with the cobalt atoms inside the lead, we still, the effect of cobalt atoms is much stronger. This is due to the spin flip, the pair as a position of cobalt atoms. And then, of course, we have this work before. Now our idea is, how about we make a superconductor of magnetic nanoparticles inside the superconductor? Of course, this line is completely randomly oriented or distributed, and if we can make simulations, it would be very interesting because then the spontaneous vortex should be what is practice. It's not what is best. Then the question is how? How to make the sample? With our machine, it's really difficult to prepare multiple layers. Very, very difficult because prepare the cobalt nanoparticles, we need to put liquid heating all the time during the preparation. So we cannot prepare very long time. Even if we want to change the viewer of the helium, we have to stop the experiment. want to prepare maybe ideas. We can prepare multi layers and by some heat treatment, they may form nanoparticles. That's at least in plane it's randomly oriented or randomly distributed, but they are one-dimensionally, they are in order. So that's why we prepared the multi-layers in the other core. We didn't prepare many samples with different thickness. Here we choose 100 nanometers neon for sure to have a superconducting neon layer. And then we